Afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to my latest training video. In this video, I'm going to talk about wind formation. All right, so let's go ahead and start and take a look at the overview of this training video. We're going to look at circulation scales. We'll look at the review of forces impacting wind. We have covered some of these already, so it will be a review of many of these. And then we'll dive into tertiary circulation, and then finally we'll conclude the training video with local scale circulation. Okay, so starting things off by looking at the circulation scales. There's a wide variety of scales, that wind blows along. There's different features on the Earth. In the atmosphere in general, we have the global scale as the largest scale, and it ranges all the way down to the micro scale. Now, for the global scale, the size of the global scale is greater than 2,000 kilometers. The time frame that the global scale covers is several days to several weeks. And examples of the global scale, some of the atmospheric features for the global scale would include your jet stream axis, the semi-permanent pressure systems that we talked about in my last video. For the synoptic scale, the size ranges from 200 to 2,000 kilometers, and the time period synoptic scale covers is tens of hours to several days. And some examples of some atmospheric features on the synoptic scale include frontal systems, and tropical cyclones would be on the synoptic scale. Working our way downward now, we look at the mesoscale circulation. So let's look at that. The size of the mesoscale circulation scale is generally 2 to 296 kilometers. The time frame of mesoscale is tens of minutes to several hours. And examples in the atmosphere of mesoscale type processes or features would include thunderstorms as well as those land sea breezes. And then finally, let's examine microscale. The size of the microscale is the smallest, generally covers, an area less than 2 kilometers. The time frame of microscale is a few seconds to a few minutes. And then the examples of microscale include thunderstorm updrafts and downdrafts. So you can see there's a large variety of atmospheric features from global scale, the largest scale, covering greater than 2,000 kilometers, right on down to the microscale. All right, so now that we've kind of talked about circulation scales, let's now do a review of forces impacting the wind. Recall from my previous training video that the pressure gradient force, it's abbreviated with the letters PGF, starts the wind blowing from higher toward lower pressure at right angles across the isobars. And remember, the isobars are lines of equal barometric pressure. So pressure gradient force gets the wind going from higher toward lower pressure at right angles across these isobars. Now, one thing again to remember is the wind speed and the pressure gradient force are directly related. So stronger wind speeds generally occur as a result of stronger pressure gradient force. The pressure gradient force is always going to be directed from high toward lower pressure. Another force we examined in a previous training video is the Coriolis force, and you'll see it abbreviated with the letter COF. Now, the Coriolis force measures the effects of Earth's rotation, and it's an apparent force which acts on moving objects due to the Earth's rotation, and it's generally considered to be relative to moving objects not fixed to the Earth. So anything not fixed to Earth, let's say something's passing, like an air parcel is on a specific path or trajectory above the rotating Earth beneath it, this is going to result in a deflection of the air parcel to the right of its intended path. In the northern hemisphere, it would be to the left of its intended path in the southern hemisphere. So again, it's relative to moving objects not fixed to Earth. The Coriolis effect, by the way, has no effect on wind speed itself, only the wind direction, and then the Coriolis is affected by the wind speed. Additionally, we examined centrifugal force in the past. Now, this is an apparent force that deflects winds away from the center of rotation. And you have felt this force many, many times when you go around a curved exit ramp. This force is going to be that force, the centrifugal force is that pull that you feel in a car going around a curve. It's going to pull you in the opposite direction of your turn. All right. Additionally, we talk about the upper levels of the atmosphere. Let's go above the surface, above the ground. We talk about curved flow. We have these geostrophic winds that can be over or underestimated. And let me just do a quick review with you on geostrophic winds. Okay, geostrophic winds. You are going to find these winds above the friction layer, so in the upper levels of the atmosphere. And in the upper level atmosphere, you have these height contours. Here, let me just draw this out. So let's say these solid red lines are your height contours, right? A geostrophic wind occurs when your wind direction, because there's no friction, is going to blow parallel to these height contours, right? That's a geostrophic wind. A geostrophic wind means things are in balance. Now let's say that this top red solid line represents, let's just do this. Let's call it 500 and let's say 510 decameters. And then let's say this next line, let's say it's, we'll just throw it out there. Let's say it's 540 decameters. You're going to have, for geostrophic wind balance, for the geostrophic wind, you're going to have contour gradient force working its way from higher to lower heights, being balanced by Coriolis force, which is going to act to the right of this intended wind flow. So when you have geostrophic wind, it occurs when the Coriolis force, I'll just draw it out as letter COF, is the abbreviation for Coriolis force, is going to act to the right of this wind direction in the northern hemisphere. That Coriolis force is going to be in perfect balance in opposite direction to the contour gradient force. So let's say this is your air parcel where I put the X, and then we have the contour gradient force, again, is always going to act from higher to lower heights in the upper levels. And that CGF and Coriolis force are balanced. That is a geostrophic wind. It blows parallel to your height contours above the surface because we don't have any friction to really turn those winds across height contours. The wind just blows parallel to the height contours when it's in a geostrophic balance or a geostrophic wind overall. All right, now moving on to forces impacting lows or troughs. Let's look at the wind forces around low pressure or troughs. Let's stay in the upper level chart. So let's say this L on the right hand side represents upper level low, height center, okay? Around lows or these low height centers or troughs, centrifugal force creates a cyclonic gradient wind, and this is going to be known as a subgeostrophic wind because it is weaker than a geostrophic wind. So what do we have going on in this case with wind forces around lows or troughs? We have the pressure gradient force, or the contour gradient force, you could substitute it with a CGF on the upper level charts, is generally equal to the Coriolis force plus centrifugal force. Okay? Now keep in mind, this is going to most likely be that cyclonic curve flow. So centrifugal force is working with Coriolis force and against the contour gradient force. You can see it over here on the right. So let's say, and I'm going to circle these as I talk about them, all right? So this is our low height center. It's represented by the letter L. And realize that the contour gradient force, CGF, or this pressure gradient force, if you're at the surface, is always going to act towards lower heights or lower pressure. So you see that this pressure gradient force is acting towards the center of this low. Meanwhile, you have the Coriolis force. Okay, if we're on the upper level chart, remember, geostrophic wind is going to blow parallel to this solid dark line here, because this solid dark line represents your height contour. So pressure gradient force, or in this case contour gradient force, is acting inward towards this low. But we have Coriolis force, which is going to turn these winds blowing parallel to these height contours to the right of their intended path. So that's going to act in this direction. And then you also have centrifugal force, because we're talking about wind blowing in a curved flow. And we talked about centrifugal force being that force that deflects winds away from the center of rotation, right? Well, this low L is the center of rotation around this turning point, or around this curved flow. So in this case, contour gradient force or pressure gradient force is going to be equal to Coriolis force and centrifugal force. All right. When we talk about wind forces impacting highs or ridges, things are a little bit different here. So around highs or ridges in the upper levels, centrifugal force is going to act outward away from the curved flow, from the center of the turning radius. All right. And that centrifugal force creates an anticyclonic gradient wind. This is known as supergeostrophic winds, super being stronger than the geostrophic wind. And what we have going on with wind forces around highs or ridges, we have the Coriolis force, which in this case, let's see, we've got a high pressure system now, so our wind circulation is going to be clockwise like this. Okay. All right, so the Coriolis force is always going to deflect this wind to the right of its intended path. Meanwhile, the contour gradient force and the centrifugal force are acting outward away from this curved flow. And that's going to result in supergeostrophic winds. So the review of forces impacting wind continues now. We talked a little bit about flow around and curved flow, winds around curved flow with lows and troughs and ridges and highs. Now let's talk about on the surface again, where we have this force of friction. Now friction exists only within the lower levels, up to about 1 kilometer within what's known as the planetary boundary layer, the PBL. Let me go back here. This frictional force opposes motion and acts opposite the wind direction. For example, let's say the wind is from the east at 090 degrees, from 090 degrees, then friction would be acting opposite to this direction. So this friction is going to be the reason why the wind blows across isobars at an angle from high to low pressure on the surface, because we have friction that's slowing the wind speeds down. All right, so here's an example on the left. We have wind direction and speed without friction, generally working its way from left to right with this particular area here on the left. And then on the right, with friction, the wind direction changes flowing across isobars, and the wind speed is going to be reduced with friction. So friction overall reduces the wind speed and changes the wind direction. If friction does increase, the wind direction will back. When I say backing winds, basically those winds are turning in a cyclonic manner or counterclockwise turning of the winds. Now above the planetary boundary layer, this PBL, friction is negligible. So once you get above 1 kilometer above the ground, you no longer have friction coming into play. The wind's going to become more geostrophic, where it blows parallel to those height contours I talked about a few slides ago. And this contour gradient force, when we're talking about height contours in the upper levels, will be on its left and Coriolis force on its right. And we talked about that geostrophic wind, which we already discussed. So at the surface with friction, the wind speed's reduced. It reduces the Coriolis force, because we talked about Coriolis force is related to the wind speed, right? So these two do kind of relate with each other. If I decrease my wind speed, that means my Coriolis force, my turning of those winds, is going to be less. The weaker Coriolis force, in this case, no longer balances the pressure gradient force, and the wind is going to blow across the isobars towards lower pressure. And then the pressure gradient force is now balanced by the sum. You add up both frictional force and Coriolis force together. The boundary layer convergence is a result, and it's associated with wind blowing in toward the low pressure. We get that low level converging air. Boundary layer divergence, by the way, is associated with wind blowing outward away from the center of high pressure. So just again, a review of forces impacting the wind. This is boundary layer divergence on the very left. You see the H representing the center of high pressure at the surface. You notice how the winds blow outward and away from the center in a clockwise manner, away from high pressure, the center. So this results in boundary layer divergence around a high. Boundary layer convergence is right next to it, just to the right of the high pressure diagram, showing the wind blowing across these solid black lines. These solid black lines represent lines of equal barometric pressure. They're known as isobars. So the wind is blowing in towards the center of low pressure and blowing across these isobars, lines of equal barometric pressure. This results in boundary layer convergence, BLC. And then over here on the right, we're showing you just the examples at the surface. As the wind blows across the surface, we introduce FR, which is friction. It's abbreviated friction, FR. We have pressure gradient force from high to low pressure. And we have Coriolis force acting opposite of that wind direction, or not opposite, to the right. Coriolis force acting to the right of the wind direction, and then the friction opposite to the wind direction overall. But overall, what you get is winds that slow and back due to friction, and they're going to blow. You notice how these arrows here on this low pressure diagram, boundary layer convergence, how they work across these isobars at an angle. And that's due to the frictional effects. So a review, here's a nice summation of the table. I think this is not quite yet. We'll get to tertiary circulations here in a moment. I thought this might be my last slide on review of forces impacting the wind. But this is a nice summation table. We have the force, the wind speed, and the wind direction. And so the impacts of what force it is, the wind speed, and impacts of it on wind speed and direction. So pressure gradient or contour gradient force initiates the wind. It does have an effect on the wind speed, so yes, that's a yes. Wind direction, also yes. When we're talking about pressure gradient force and wind flowing on the surface, we are going to have frictional impacts there. So yes, basically the wind's going to work its way toward low pressure, the center of the low pressure across the isobars. Centrifugal force, it acts outward in curved flow. It does not have any effect on wind speed, but it does have an effect on wind direction. Coriolis force always acts to the right of the direction, 90 degrees to the right of direction of the wind. It does not have an effect on wind speed, but it does have an impact on the wind direction. And then friction slows and backs the wind. So it does impact your wind speed, it slows it down, and it does kind of change your wind direction due to that friction. So friction is the only force that affects and is affected by wind speed. So this is a nice summation table that we put together here for you to kind of get a summation of everything we covered, between pressure gradient force, contour gradient force, centrifugal force, Coriolis force, and friction. Remember, with friction, you only have to worry about that at the surface, where you have the wind blowing across the ground and around buildings and big cities, and it's going to slow that wind speed down. It's going to change its direction. With the same pressure gradient now, surface wind is going to move more slowly than the geostrophic wind. And we'd expect that, right? Because on the surface, again, we have friction, which is slowing the wind speed down. On the upper levels of the atmosphere, we have a geostrophic wind. There's no friction slowing that wind speed down. So this makes a lot of sense. Now, the strength of the boundary layer convergence and boundary layer divergence, or the angle at which the wind crosses these lines of equal barometric pressure, these isobars, as well as the height of this planetary boundary layer, are really going to depend on three main factors here. Terrain is one of those factors. The rougher the terrain, the greater the friction is going to be, and the higher what's known as that planetary boundary layer is going to be. Now, just remember, PBL, planetary boundary layer, is just that layer of the atmosphere from the surface to a 1 kilometer that basically friction is a factor. Wind speed is also a factor. The stronger the wind speed, the greater the friction, and the higher that planetary boundary layer is going to be in depth. And then stability. The more unstable the air, the greater the friction, the higher the planetary boundary layer, the PBL. So these are the three main factors that really impact the strength of boundary layer convergence into low pressures at the surface and boundary layer divergence out of high pressure at the surface, or the angle at which the wind's going to cross these isobars, as well as how tall that planetary boundary layer is. The terrain is a big one, the wind speed as well. and then stability. What's the atmospheric stability like in any one particular day? Finally, let's talk about tertiary circulations. Now, these are thermally induced and they're driven by local heating and cooling. These circulations require weak opposing pressure gradients. And if you have an opposing pressure gradient that's too strong, these circulations will not set up. So the way I like to think about tertiary circulations in the atmosphere would be like the sea breeze, land breeze effect. You're not really going to get a sea breeze in the wintertime. And the main reason that is because your synoptic pressure gradient is too strong. So it's going to overpower this smaller scale tertiary circulation. Here are your tertiary circulation types: the sea or the lake breeze if you live near a lake, the land breeze. In addition, in mountainous areas, the valley breeze as well as the mountain breeze is a tertiary circulation type. Again, you aren't really going to see this very often in the wintertime because your synoptic scale pressure gradient is just so strong it overpowers these smaller scale effects. Now, these do show up quite well in the summer season when our overall synoptic pressure gradient is much weaker. So these generally tend to take over in the summertime. So the sea or the lake breeze, let's talk about that first. The sea or lake breeze occurs when you have uneven heating taking place between the land and the nearby water. Bottom line, land heats up and cools down much faster than water. So during the day, that land heats up more quickly than the adjacent water next to it. And this sets up a shallow thermal or heat low over land. You get rising vertical air motion over land because the air is hotter and less dense. And you get the air to move in from the lake or the sea breeze or the lake breeze, that the air is coming in from the water, replacing the rising air over the land. So you get air over the water that's cooler than the air over land, and that develops this thermal high above the water with sinking air motion. The sea or lake breeze then is going to blow from the water toward the land during the day. And it generally develops in the late morning, but really kicks in. It reaches its peak strength during the afternoon hours when the heating is at a maximum. So your temperature gradient between the heated land and the cooler water is much stronger in the afternoon hours. There's a greater temperature difference between the air over the land, the heated land, versus the air over the water. Now, the leading edge of this sea breeze or lake breeze is referred to as a sea breeze front and commonly leads to afternoon thunderstorms. Now, the sea breeze front definitely occurs along the Gulf Coast states, and I've also seen it happen in southern Mississippi, very common across the Florida Peninsula. You get a sea breeze front, that's the dividing line between the cooler water, the air coming in off the water, that cooler boundary there, and the heated land. The sea breeze front can be enhanced depending on the shoreline shape even. So the shape of that shoreline, if it's convex, the sea breeze front can run into itself, and that's going to enhance the low-level convergence even more and increase your thunderstorm coverage. Here's an example of a sea or lake breeze. So again, let's just take a look at this image here on the left. During the day, you got the sunshine out. It's heating this landmass much more quickly as compared to the water. And so you get low pressure or rising air motion over the land area, the heated land area. And then you notice in the upper levels here how the airflow works its way back towards above the water. And now you get this meso high during the day over the water because temperatures are cooler over the water, so the air is heavier and it wants to sink, forming this mesoscale high pressure system, mesoscale low pressure over the heated land. And look at the surface, how the air blows from the cooler water towards the heated land. See this? This is your sea breeze. Over here on the right, we're talking about like the shapes of this shoreline. So we're talking about this, if the shoreline's convex, the sea breeze can run into itself and increases that low-level converging air, increasing your thunderstorm coverage. See how this is a convex shaped shoreline here? So you can actually get these three different streams of air kind of meeting each other at this point over the heated land, which is going to enhance your sea breeze convergence in general. Land breezes now are the opposite. At nighttime, the land cools much more quickly than the water, so we flip the pressure pattern at night. So we get a mesoscale high with cooler air over land, sinking air over land. We get that air to go basically from the land area, the cooler land, back towards the relatively warmer water, the air over that relatively warmer water, and you get a mesoscale low pressure over the water. So air at night is going to flow from land toward the water. Okay, so you get higher pressure over the land, the wind blows from high to low pressure, and then you get rising air motion over the water in the vertical, and you get sinking air motion over the cooler land. So these temperature contrasts, by the way, for the land breeze, this is usually much weaker because the temperature contrast is not as great as during the afternoon with the sea breeze. Valley breezes now. If you live in an area of mountainous terrain, again, you need to have a synoptic scale pressure gradient that's weak. And this is typically going to happen during the summer season. Now, the valley breeze, it happens during the daytime. It develops during the morning hours, reaches a peak in the afternoon. The sun heats the mountain slopes, which warms the surrounding air via conduction. So here we are. Look at this picture on the right. Imagine that the sun is out right over here in this area. This incoming shortwave radiation hits this windward side of the mountain slopes, hits this side of the mountain slopes, and the air is going to rise on that side of the mountain slopes, okay? And it's going to form these clouds and potentially some precipitation on the windward side of the mountain. This is a valley breeze because as the air rises over the mountain slopes after it's heated, you're going to have the air from the valley come up the mountain slope, from the valley up the mountain slope, and that's why it's called a valley breeze during the day. So there we go. The mountain breeze, on the other hand, this happens at nighttime because what we have going on now are these mountain slopes are cooling rather quickly, and now the air is flowing down the mountain slopes for the mountain breeze at night. So the mountain slopes are cooling really quickly, chilling the air in contact with them. This cooler, denser air then is going to glide down slope into the valley, providing a mountain breeze into the valley. So the wind basically changes direction depending on whether you live on the mountain or in the valley. You're going to notice these changes in the wind direction daily, specifically in the summertime when we have, again, a weak synoptic scale pressure gradient. The mountain breeze develops just after sunset, and then it's going to reach a peak strength just prior to sunrise before the sun really comes out again. And we repeat this diurnal or daily cycle. Because gravity is a force that directs these winds downhill, these winds are also referred to as gravity winds or drainage winds. All right, that wraps up this presentation, this training video. It's interesting when we talk about, forces impacting wind. What we covered today, we talked about circulation scales, from global scale all the way down to micro scale. Now, most of the time in the wintertime, you're really going to be dealing with this global scale, atmospheric features, and synoptic scale. That's really what you're going to be seeing a lot more of in the wintertime. I know you can get frontal systems and tropical cyclones in the synoptic scale in the summer, but the frontal systems at least are not usually as strong as in the winter. But you can of course get very strong tropical cyclones, but that would be an example on the synoptic scale. Now, the mesoscale and the microscale are primarily going to occur during the summer season when your synoptic scale pressure gradient is much weaker, they're over a much smaller area. Mesoscale affects a land or a sea breeze, a mountain valley wind. Microscale would be your updrafts and downdrafts within a thunderstorm cloud. That's really going to happen a lot of times during the summer season. We reviewed the forces impacting the winds, from pressure gradient force at the surface, contour gradient force aloft, above the surface, above the effects of friction. Coriolis force, remember, turns all objects to the right of their intended path of motion in the northern hemisphere. So we're talking about air parcels, that would be an example. Centrifugal force is always going to act and deflect winds away from the center of rotation. You've probably felt this during going through a sharp turn in a car. You feel that pull outward away from the center of the curve. Geostrophic winds, we talked a little bit about that when we have the Coriolis force balanced with the contour gradient force. And then we talked about, the different types of forces around lows or troughs. We're talking about curved flow here. We have the pressure or contour gradient force. We have the Coriolis force and centrifugal force acting in the same direction in this case. And then with highs and ridges, the wind forces involved. Coriolis force, again, the pressure gradient force or contra gradient force acting in the same direction as centrifugal force. And then you have, we talked about friction at the surface within the planetary boundary layer up to 1 kilometer. This is friction will oppose motion, slow the wind speed down, and also will act opposite the wind direction. Because of friction, we have the wind that blows from high to low pressure across isobars. And it also results in the boundary layer convergence, BLC, and the boundary layer divergence with BLD. Talked a little bit about examples graphically of these. With high pressure systems, air is working outward, it's blowing outward away from the center of the high across these isobars at an angle. That's boundary layer divergence. And then with low pressures, air moving inward towards the center of low pressure across isobars is boundary layer convergence. Examples of what friction does to your wind. Generally, when talking at the surface, we have pressure gradient force and Coriolis force. But when we have friction involved, that slows the wind speeds down, and it's going to change your wind direction. Winds are going to slow and then back with friction. And then we did the summation of everything, of all the forces we talked about on this table. And then we did more review on what really impacts the strength of the boundary layer convergence into low pressure, the boundary layer divergence out of high pressure centers, the angle at which the wind crosses isobars, as well as the height. How tall is a planetary boundary layer really is dependent on terrain, wind speed, and stability. Talked about tertiary circulations, which are thermally induced, driven by the local heating and cooling of the day during the summer season. And there are some examples we talked about: sea breeze, lake breeze, as well as land breeze. And then we talked about valley breeze as well as mountain breeze. So hope you enjoyed this presentation. You learned a little bit today. That's all I got for now. I've got plenty more training videos ahead. So stay tuned to the Spot on Weather YouTube channel for more great information. Until next time, everybody, take care and God bless.